Nije to. Eto da tu crni podem. Kad?
Good afternoon. I'm going to talk about some main results from my PhD thesis. This is joint work with my mentor, Ivana. And the results are about the impact of Yarkovsky effect and motion resonances on rebuilt asteroids transcript. And this is short content of my presentation, introduction, methods, results, and some conclusions and future works. At the beginning, I had to say something about the motion resonances and Yarkovsky effect. As we know, the long-term dynamics of asteroids is governed by complex interaction among gravitational and non-gravitational forces domain. Gravitational force are mean motion resonances as a result of commiserability between orbits of orbital motion between asteroids or one or two planets. And the Yarkovsky effect is the most important non-gravitational force. This is a thermal effect that causes small objects to change their semi-major axis and to have a semi-major axis drift as a function of their orbit, spin, and diameter and other physical characteristics. And this interaction among the motion resonances and Yarkovsky effect may result in some overall change of the Yarkovsky mobility. And that was exactly our motivation for our work, because this interaction cannot be investigated yet in details. We have results about semi-major axis drift in motion resonances under the influence of Yarkovsky effect. We used some numerical and statistical methods. I will speak about some numerical methods. First of all, we used numerical integration in order to simulate and investigate transition and of asteroids across mean motion resonances. We applied this numerical integration in public domain Orbit 9 software. We used exactly 66,000 test asteroids, and of course in each simulation we included Yarkovsky drift speeds. We used, for example, 10 equidistant Yarkovsky drift speed from 10 to the power minus 5 to the 10 to the power minus 4 astronomical unit per million year. We use these values because these values are reliable for kilometer-sized asteroids in the main belt. And we track this motion of asteroids from 42 till 120 million years because of this range exists because of the different strength of our motion resonances and of course of different very wide range of Yarkovsky drift speeds. I have to first to say about numerical method which we published in these two papers about definition definition of borders in motion resonance. This is an example of one of our motion resonances in play. Semi-major axis, this is semi-major axis A, and this is E, eccentricity. This is center of the resonance, and this is very symmetrical, totally symmetrical borders in respect to the center of resonances, because we choose to use some wider values, some wider borders of resonance in respect to the in this plane, because we put at the beginning the test asteroids for each of our resonance. We made input catalog with 600 test asteroids for 10 distant equidistant Yarkovsky drift speed, and for 11 times 11 resonances we got this number. And we put this test asteroid very close to the outer border, but outside it. It's very important to say that because we put this outside, that test asteroids outside this outer border, because we wanted to see whole effect of interaction between asteroids and each of 11 motion resonances. And asteroids go from larger to smaller values because of semi-major axis, because we choose to use negative values of the positive speed, but the case is the same if we use from inner to outer border, and also with the positive values of the positive speed. And our asteroids crossed the resonance perpendicular to the borders of resonance. And I wanted to say that also the main role of Yarkovsky effect to change semi-major axis of asteroids and to force asteroids to cross mean-motion resonances. This is some figure in playing semi-major axis eccentricity about our choose 11 isolated resonances with Jupiter. We choose Jupiter because this is the largest and the most important planet in our solar system, and we decided to use, of course, isolated resonances because these resonances have very well-defined borders, and in these resonances there is no overlapping with other resonances, which is very important to exclude his influence. There is influence on semi-major axis of asteroids. And this is some basic characteristics of our mean-motion resonances. In this table, we presented in the first column their names from the most strong to the most weak strength resonances. In the second column, there are order of our resonances, and the third center of resonances in units of semi-major axis, and the fourth we present in the fourth column the strength of resonances. In order to calculate the strength of resonances, which is very important for definition of this interaction, we use this paper and formula in the numerical method, which is explained and which that applied by Yarkovsky 2006 to calculate strength of resonances of mean-motion resonances of two bodies, asteroids and Jupiter in our case. At the beginning, after numerical integrations, we had to calculate moments of entering and exiting from the resonance, T1 and T2. In the first and the second plot, also the moments of entering and exiting, and this very large amplitude of change of semi-major axis means that the asteroids spend this time, for example, from 60 to 100 million years in resonances, and in this part of semi-major axis there is no resonances, and objects our objects are out. I think one object is out of resonances, and we define at the beginning this value, visible value delta t, but after, and we got some result with this delta t value, but we decided to use some change the time that object spent in the resonance, because we wanted to isolate the influence of mean-motion resonances on asteroids across that resonances, and delta R is the structural difference between latest semi-major axes respectively at these two moments, T1 and T2, and this is the Yarkovsky drift speed. And there is the first our result. In the upper plane, we can see approximately linear functional dependence between the strength of resonances which are in this plane. This is in this logarithmic plane. As we can see, this dependence is linear, and that means that the functional relation that describes this dependence is exponential function. Also, we have, I have to say that this value is for the weakest resonance, and is for the, of course, for the strongest resonance. And we have here increasing strength, increasing time. That object spectral resonance with increasing of semi-major axis. In the lower plane, in the lower panel, we have plane of Yarkovsky drift speed. And it's a plane of VTR as a function of Yarkovsky drift speed. We have a very similar but opposite trend between these two values. We have here increasing of times, and we have here increasing also in the plane of Yarkovsky drift speed and VTR. We have some exponential function that best describes this relation. And we published in this paper this equation. We proposed this equation as the best equation that fit our data in this previous plot. And after logarithmic this equation, we got this linear equation in logarithmic plane, and we applied after that a numerical method of linear least squares to fit our data with this equation in order to get these three unknown coefficients, C1 and beta and gamma known exponents. And we got two results for 11 resonances and for 6 resonances. Why? Because we noticed that there is some distinction between the weakest and strongest resonances, and we wanted to check why that was exist, and because we know that it's a very poor ratio between signal to noise for our weakest resonances, but we got very good results for 11 and for the 6 the strongest resonances. We can compare these results. The values are very similar, and not only very similar but statistically the same, with very small errors. And because of that, because of these similar results between these two groups of resonances, we wrote this very simple equation that explains a relation between Yarkovsky drift speed, strength of resonances, and time that objects spent in the resonance. And from this equation, that because of Yarkovsky drift speed is inversely proportional to the diameter of asteroids, we got that this time is proportional to the diameter of asteroid. But it is not very correct, because I read some paper a few days ago that is the authors published that this physical value, this Yarkovsky drift speed, is not simply inversely proportional to the diameter, and they investigated this relation, and they will publish, I think, very soon. This relation is not only a simple inversely proportional between Yarkovsky drift speed and diameter of asteroids. Also, as we know, strength of resonances depends, very strong depends on eccentricity, and we can see in these two papers about this dependence. And because of that, we calculate this equation. We calculated strength of resonances. We have 10 equidistant Yarkovsky drift speed, and after applying numerical method for strength of resonances and the linear least squares method, we got for this these different values of eccentricity from 0.025 with this step to 0.4 these values, but we got here very interesting results about all three unknown exponents and coefficients. The first dependency is between eccentricity and beta for this range of eccentricity from the table, and we can see in this plane that this dependency is exactly linear dependence, and we got this unknown coefficient for all resonances. The same situation is also for 6 resonances. And I had to switch on this table because I have to say about this coefficient gamma, because we have constant values of Yarkovsky drift speed, we always got constant values of gamma which connects our DTR and Yarkovsky drift speed. There is also very small difference between the standard errors of these coefficients. And in this plot we got a functional relation between eccentricity and the unknown coefficient, and we got some oscillations around the linear trend. When I write this linear, when I fit this data with a linear equation, I saw the clear oscillations about that sinusoidal oscillation about that linear trend. We don't know because what it means, and we decided for now to read the values of this coefficient C2 from the table, and also there is some distinction for the smallest value of eccentricity, and because of that we decided to use values from this table previous for C2. And that was this, and in this way we established equation for the first time. We established functional relation between the strength of resonance and Yarkovsky drift speed, eccentricity, and the time that objects spend in resonance. Also, we have some idea to include inclination in this equation, but we will see. And the other one, I can say the other main result in my PhD thesis is about distribution of DTR, because we wanted to further investigate this dependence between the interaction between motion resonances and the Yarkovsky drift speed. We calculate distribution of DTR. We used histograms in order to see something facts about our distribution of our time, and this is for our 4 resonances. Of course, we applied the Kolmogorov-Smirnov test for 2 samples in order to check whether our 2 samples have the same or the similar distribution, and the result was positive. Our data here is, as you can see, very similar distribution. There is some difference between for the slowest Yarkovsky drift speed. And this is the plane of time that objects spent in resonances and the number of objects for all our 10 different Yarkovsky drift speed. And after many trials, which statistical distribution functional density the best fit our distribution of DTR of our data, we decided to use this modified Laplace distribution function with this branch, and this is definition about that function, and and this is the definition of about 5 parameters following the shaping and this of the parameter of location. And of course, after that, we had to apply some statistical tests in order to check whether our distribution is good, is appropriate for our data. And we used the very well-known Pearson's chi-square model, and the result was positive for bottom branch of our multiple symmetric function. And this is the first part, and this is the second part of the same picture about the same resonance 9-4 with Jupiter in the same plane. And we have a very good fit of this function. On the same result is for all other resonances and the Yarkovsky drift speed. I will briefly say something about that. This is our 8 most important results from this distribution function about connection between this parameter of distribution L, K, and for right and left branch, and their connection, center resonances, and the Yarkovsky drift speed. We have a very clear sum connection between these two parameters and these two R values, and also between these two parameters and these two R values. We decided to use this equation as a best equation to fit this data from these two pictures. After applying again the numerical method of linear square, we got this result for unknown coefficient ABC. And for these 4 parameters of our distribution. When we know these 3 unknown coefficients and center of resonance and Yarkovsky drift speed, we can very easily calculate these unknown parameters of our distribution. Conclusions, this is the first general equation between eccentricity, center of resonance, Yarkovsky drift speed, and that entanglement with object spent in motion resonances. Also for this range of eccentricity is variable. And this is the second main result about this asymmetric distribution function. That's all. I wanted to say some about future works. I forgot to write about that. We plan to simulate moving of asteroids across mean-motion resonances for Jupiter and Saturn, and also we got some new results about interaction between our 11 mean-motion resonances, but with the other range of Yarkovsky drift speed, which is smaller than 2-4 astronomical unit per million year, and so on. Thank you.
Thank you. For one question, maybe 2, please. If not, thank you again. Finished, and now is coffee break, and next session will start.